Did you know that many AWS Certified Welding Inspector candidates don't fail because they can't weld? They fail because they misunderstand the inspection principles behind the welding process. A single wrong answer about how a weld is made can cost valuable exam points and, in the real world, lead to expensive defects or serious safety risks. That's why this first section is one of the most important parts of your entire CWI preparation. By the end of this lesson, you'll understand the welding fundamentals and the most common welding processes every successful welding inspector must know before evaluating weld quality. Be sure to download the free CWI study guide linked in the description, where you'll find some of the most important exam questions to reinforce what you learn in this course. Now, let's begin building the strong foundation that will help you move through the rest of the course with confidence and bring you one step closer to earning your AWS Certified Welding Inspector certification. We will start with shielded metal arc welding, which most people simply call stick welding. This is one of the oldest and most widely used welding processes in the world because it is highly portable and versatile. In stick welding, an electric current is used to strike an arc between the base metal and a consumable electrode rod. This intense heat melts both the base metal and the electrode, fusing them together to form a solid joint. You will often see this process used in field construction and pipeline work because the equipment is relatively simple and requires no external shielding gas tanks. The secret to stick welding lies in the flux coating that surrounds the metal electrode rod. As the intense heat of the arc melts the rod, this solid flux coating burns and creates a protective gas shield around the molten weld pool. This gas shield prevents oxygen and nitrogen in the atmosphere from contaminating the liquid metal, which would otherwise cause severe porosity and structural weakness. After the weld cools, the remaining flux forms a solid layer over the weld called slag, which the welder or inspector must physically chip away. For your exam, remember that the inspector must ensure all slag is completely removed before the final visual inspection can take place. Next, let us discuss gas tungsten arc welding, frequently referred to as TIG welding. TIG stands for tungsten inert gas, and it is known for producing the highest quality and most visually appealing welds of all the standard processes. Unlike stick welding, this process uses a non-consumable tungsten electrode to create the arc. Non-consumable means the tungsten does not melt into the weld pool, but simply acts as a torch to melt the base metal. Because the electrode does not provide filler metal, the welder must manually feed a separate filler wire into the weld pool if extra material is needed to build up the joint. Since there is no flux involved in gas tungsten arc welding, the molten metal must be protected by a constant flow of shielding gas, usually argon or helium. This gas flows directly out of the welding torch, covering the hot tungsten and the liquid weld pool to keep atmospheric contaminants away. This process requires a very high level of operator skill because the welder must use both hands independently, one holding the torch and the other feeding the wire. As an inspector, you must watch out for a specific defect called tungsten inclusion, which happens if the welder accidentally dips the tip of the tungsten electrode into the liquid metal. Now we will move on to gas metal arc welding, commonly known as MIG welding. This process is heavily used in manufacturing and fabrication shops because it is incredibly fast and highly efficient. In this method, a continuous solid wire electrode is automatically fed through a welding gun by a mechanical wire feeder. This wire acts as both the electrode to create the arc and the filler metal that builds up the weld joint. When you press the trigger on the welding gun, the wire feeds continuously, allowing the welder to complete long welds without stopping to change rods like they have to in stick welding. Just like TIG welding, gas metal arc welding requires an external shielding gas to protect the molten weld pool from the surrounding air. This shielding gas flows through the welding gun and surrounds the wire as it melts into the joint. A common exam topic is understanding that because MIG welding relies on an external gas cloud, it is highly sensitive to wind or drafts. If a strong breeze blows the shielding gas away during welding, the weld will instantly become contaminated with atmospheric gases, leading to severe porosity. Therefore, you will rarely see standard MIG welding performed outdoors on a windy construction site. Closely related to MIG welding is a process called flux cord arc welding. This process also uses a continuous wire feed system, making it just as fast and efficient, but the wire itself is completely different. Instead of a solid metal wire, flux cord welding uses a hollow tubular wire that is filled with dry flux compounds inside. As the wire melts, The internal flux burns and creates both a shielding gas and a protective slag over the weld, very similar to how a stick electrode works. This ingenious design combines the high speed of wire-fed welding with the rugged outdoor capabilities of stick welding. Flux-cored arc welding actually comes in two different variations, and knowing the difference is an important exam concept. The first variation is self-shielded, which relies entirely on the flux inside the wire to protect the weld pool, making it excellent for windy outdoor conditions. The second variation is gas-shielded, which uses the internal flux plus an external shielding gas from a tank to provide double protection. The gas-shielded version produces smoother welds and is heavily used in heavy equipment manufacturing and shipbuilding. As an inspector, you must verify that the welder is using the correct variation specified on the qualified welding procedure. Another highly productive process you must understand is submerged arc welding. This is an automated or semi-automated process typically used for welding thick plates of steel in straight lines or massive circles. The most unique feature of this process is that the arc is completely buried, or submerged, under a thick blanket of granular flux. A mechanical hopper constantly pours this sand-like flux over the joint just ahead of the continuously fed wire electrode. Because the arc is completely hidden beneath the flux, there is no visible light, no flying sparks, and very little welding smoke produced during the operation. The granular flux in submerged arc welding performs multiple vital functions. The flux immediately surrounding the arc melts into a liquid, protecting the weld pool and cleaning the molten metal of impurities. The unmelted flux on top acts as an incredible thermal insulator, trapping the heat deep inside the metal and allowing for massive deposition rates. After the machine passes, the molten flux cools into a thick slag crust that easily peels away to reveal a perfectly smooth weld. In your exam, remember that submerged arc welding is generally limited to flat or horizontal positions because the granular flux would simply fall off if used vertically. To inspect these processes properly, you must grasp basic welding electricity, specifically the difference between voltage and amperage. Think of electricity like water flowing through a garden hose. Voltage is the pressure pushing the water, and in welding, voltage directly controls the length of the arc and the width of the weld bead. Amperage is the volume of water flowing through the hose, and in welding, amperage directly controls the melting rate of the electrode and how deeply the heat penetrates into the base metal. If a welder sets their amperage too high, they risk burning completely through the metal. You also need to understand the types of electrical current used in welding machines. Direct current, or DC, flows continuously in only one direction and provides a very smooth, stable welding arc. Alternating current, or AC, constantly switches direction back and forth many times per second. Most industrial welding uses direct current because it produces less spatter and creates a cleaner final product. However, alternating current is specifically used when TIG welding aluminum, because the rapid back and forth action of the electricity physically breaks up the tough oxide layer that forms on the surface of aluminum parts. When using direct current, the direction of the electrical flow is called polarity, and it greatly affects the shape of the weld. Direct current electrode positive means the electricity flows from the metal plate up into the welding rod, which concentrates most of the heat directly on the tip of the electrode. This causes the rod to melt quickly, allowing for deep penetration into the joint. Direct current electrode negative means the electricity flows from the rod down into the plate, which puts more heat into the base metal itself. Knowing which polarity to use is a fundamental requirement found on any standard welding procedure document. Before a weld can be made, the metal pieces must be prepared and arranged into a specific joint design. There are 5 basic welding joint types that you must memorize for the CWI exam. These are the butt joint, the corner joint, the T-joint, the lap joint, and the edge joint. A butt joint simply places 2 plates edge to edge on the same plane, while a T-joint places 1 plate vertically on top of a horizontal plate. Forming the letter T. Identifying these joint configurations accurately is the very first step in determining what kind of weld needs to be applied and how to inspect it. Once the joint is assembled, the welder applies a specific type of weld. The 2 most common types you will inspect are groove welds and fillet welds. A groove weld is made in the space or gap between 2 overlapping or adjoining pieces of metal, and is heavily used in butt joints to fuse the entire thickness of the plates together. A fillet weld is roughly triangular in shape and is used to join two surfaces that sit at right angles to each other, like in a T-joint or a lap joint. Over 80% of all industrial welds are fillet welds because they require very little edge preparation before welding. Welding position is another critical variable because gravity drastically affects how the liquid metal behaves in the weld pool. The four basic welding positions are flat, horizontal, vertical, and overhead. The flat position is the easiest and most preferred because gravity helps keep the molten puddle naturally resting inside the joint. The overhead position is the most difficult because gravity constantly tries to pull the liquid metal down onto the welder. For certification purposes, a welder who passes a performance test in the difficult overhead position is generally qualified to weld in the easier flat and horizontal positions as well. Every welding code strictly defines what we call essential variables. An essential variable is any change in the welding setup that will directly affect the mechanical properties or strength of the final weld. Examples of essential variables include changing the welding process from stick to TIG, changing the type of base metal, or significantly changing the electrode thickness. If an essential variable is altered on the job site, the existing welding procedure becomes invalid, and a completely new qualification test must be performed. A major part of your job as an inspector is verifying that the welder stays within the approved essential variables at all times. As a certified welding inspector, you are not required to be a perfect welder yourself, but you must completely understand how these processes operate. You must be able to look at a completed weld and immediately recognize if the voltage was too low, if the travel speed was too fast, or if the shielding gas failed. Knowing the mechanics behind stick, TIG, MIG, and submerged arc welding allows you to identify the root cause of visual defects accurately. This theoretical knowledge is what separates a simple observer from a highly qualified welding inspector who can solve real problems in the field. Congratulations on completing this first section on welding fundamentals and processes. I strongly encourage you to complete the attached practice test right away. Completing practice questions immediately after the lesson improves your memory retention and builds serious exam readiness. The practice test is included with this lesson, so take full advantage of it to reinforce your active learning and lock in these concepts. Once you have conquered those questions, we will naturally transition into the fascinating world of welding metallurgy and base materials in the next section. End this session positively, take a quick break, and I will see you in the next lesson. Welcome back to the course, and welcome to our second section covering welding metallurgy and base materials. In this lesson, you will learn the fascinating science behind how metals react when exposed to extreme welding heat. Understanding metallurgy is absolutely critical because it allows you to predict how a weld will perform under stress and why it might fail. I am thrilled to share this topic with you because seeing metal at a microscopic level completely changes how you look at the welding process. Get comfortable, prepare to expand your mind, and let us dive into the hidden world of metals. Metallurgy is simply the study of metals, their physical properties, and how they behave under different conditions. When we talk about welding metallurgy, we are specifically looking at how the rapid heating and cooling cycle of a welding arc changes the internal structure of the base metal. You might think of a steel plate as a solid, unchanging object, but under extreme heat, it is actually a dynamic material that constantly transforms. As an inspector, knowing these transformations helps you understand why specific procedures must be followed on the job site. To understand metal, you have to imagine it at the microscopic level. Solid metals are made up of tiny crystalline structures called grains, which tightly pack together like a microscopic puzzle. The size and arrangement of these grains directly determine the physical strength and flexibility of the metal. When you heat metal up with a welding torch, these grains actually change size and shape, which permanently alters the strength of the material. Your goal as an inspector is to ensure the welding procedure keeps these microscopic grains as healthy and strong as possible. The most common material you will inspect in your career is carbon steel. Carbon steel is essentially an alloy made primarily of iron, mixed with a very small amount of carbon. Even though the carbon amount is tiny, usually less than 1%, it is the most powerful ingredient in the recipe. The exact amount of carbon inside the steel dictates almost everything about how the metal will behave when someone tries to weld it. The rule for carbon is very straightforward, so keep this in mind for your exam. The more carbon you add to iron, the stronger and harder the steel becomes, but it also becomes much more brittle and difficult to weld. Low-carbon steel, often called mild steel, is very flexible, easy to weld, and rarely cracks. High-carbon steel is incredibly strong for making tools or springs, but if you try to weld it without special precautions, it will easily crack like glass. This brings us to a vital industry concept called weldability. Weldability simply describes how easily a specific metal can be welded without cracking or losing its structural integrity. Engineers use a mathematical formula called the carbon equivalent to determine the weldability of a piece of steel. If the carbon equivalent number is high, the inspector knows the welder must use special heating techniques to prevent the joint from failing. Besides carbon, steel manufacturers add other ingredients called alloying elements to improve the metal. Two common alloying elements you will see on the exam are manganese and silicon. These two elements are known as deoxidizers, meaning they actively fight off oxygen and help clean the liquid weld pool. Adding manganese also significantly increases the overall tensile strength of the steel, making it a very popular addition in modern construction materials. You will also encounter stainless steel, which behaves very differently from standard carbon steel. Stainless steel gets its famous rust resistance from a heavy dose of chromium and nickel added to the mixture. The chromium creates an invisible, microscopic shield on the surface of the metal that stops oxygen from creating rust. However, these elements make stainless steel very sensitive to heat buildup, so welders must travel quickly to avoid warping the metal. Let us talk about what happens when you heat metal up, which is a process known as thermal expansion. When metal gets hot from a welding arc, it physically expands and grows larger. When the welding is finished and the metal cools down, it contracts and shrinks back to its original size. This constant expanding and shrinking acts like a powerful invisible muscle, pulling on the metal plates and causing them to warp or bend out of shape. This shrinking process leaves behind something called residual stress. Residual stress is a trapped, invisible force locked deep inside the metal joint after the weld has completely cooled to room temperature. Imagine stretching a thick rubber band and locking it in place. That tension is similar to residual stress. If the residual stress becomes too high, it can literally rip the weld apart from the inside out, causing a massive failure long after the welder has gone home. The most critical area you will inspect is called the heat-affected zone, commonly abbreviated as the HARZ. The heat-affected zone is the narrow band of base metal immediately next to the weld that did not melt, but got extremely hot. Because this zone experienced high heat and rapid cooling without actually melting, its microscopic grain structure is completely altered. In almost all welded structures, the heat-affected zone is the weakest link and the most common place where cracks begin to form. Inside the heat-affected zone, the extreme heat from the arc causes the microscopic metal grains to grow very large. In metallurgy, large grain sizes usually result in a weaker, more brittle material. This grain growth is a major reason why engineers carefully control how much heat a welder is allowed to put into the joint. By keeping the welding heat strictly controlled, you prevent the grains in the heat-affected zone from growing too large and weakening the structure. The speed at which a weld cools down is another massive factor in metallurgy. If a welded joint cools down very slowly, the steel remains soft, ductile, and flexible, which is exactly what we want. However, if a weld cools down too rapidly, the steel instantly transforms into a very hard, brittle microscopic structure called martensite. Martensite is dangerously brittle, and if a weld cools fast enough to form it, the joint is highly likely to crack under pressure. To prevent this rapid cooling, the industry uses a technique called preheating. Preheating simply means using a large torch or electric blankets to warm up the base metal before any welding begins. By starting with a warm piece of metal, the final weld cools down much slower, preventing the dangerous, brittle martensite from forming. As a welding inspector, checking the base metal with a temperature thermometer to ensure proper preheat is one of your most important daily tasks. One of the most dangerous defects caused by poor metallurgy is called hydrogen-induced cracking. For this specific crack to form, three things must be present at the exact same time, which are a brittle microscopic structure, high residual stress, and hydrogen gas trapped inside the metal. Hydrogen gas is incredibly tiny and can easily slip into the liquid weld pool, where it gets trapped as the metal freezes solid. Once trapped, the hydrogen slowly builds up immense internal pressure until the cold steel simply snaps. To fight hydrogen cracking, welders use special low hydrogen electrodes. These electrodes are manufactured with absolutely no moisture in their flux coating, because water is the primary source of hydrogen gas. However, if these electrodes are left sitting out in the humid open air, they will quickly absorb water like a sponge. This is why you will always see low hydrogen stick electrodes stored in specialized heated ovens on the job site, and you must strictly enforce this rule as an inspector. Sometimes, preheating is not enough to protect the metal, and we must use post-weld heat treatment. Also known as stress relieving, this process involves placing the completely finished weldment into a massive furnace and baking it at a high temperature for several hours. This baking process safely relaxes those locked-in residual stresses and softens the heat-affected zone back to a safe level. This is commonly required for thick pressure vessels and heavy piping systems to ensure they do not crack in service. When reviewing test reports, you must understand the basic mechanical properties of metal. Tensile strength measures how much pulling force a metal can take before it breaks in half. Yield strength measures how much force it takes to permanently bend the metal so it will not spring back to its original shape. Ductility measures how much the metal can stretch and deform without snapping, which is a highly desirable trait in earthquake-resistant buildings. Two other crucial properties you will see on the exam are toughness and hardness. Toughness is the ability of a metal to absorb a sudden, violent impact without shattering, which is usually tested using a swinging pendulum called the Sharpe V-notch test. Hardness is a metal's ability to resist dents, scratches, and wear on its surface. Typically, as a metal becomes harder, it loses its toughness, which is a constant balancing act that engineers must manage when designing welded structures. Congratulations on completing this challenging section on welding metallurgy and base materials. I strongly encourage you to complete the attached practice test right now while the information is fresh in your mind. Practice questions dramatically improve your memory retention and build the true exam readiness you need to succeed. Remember that the practice test is included with this lesson, so use it immediately to support your active learning journey. I am proud of your progress, and after you finish the quiz, we will naturally transition into destructive and non-destructive testing in the next section. Welcome back to the course, and welcome to our third section where we will explore destructive and non-destructive testing methods. In this lesson, you will learn how we physically break and safely scan welds to evaluate their true internal strength. This is incredibly important because a welding inspector must know exactly how to prove a weld is safe for public use before signing any approval documents. I am very excited to show you these evaluation tools because they are the core techniques used by elite inspectors worldwide. Let us jump right in and discover how we truly test metal. We will start by discussing destructive testing, which is exactly what it sounds like. Destructive testing involves physically breaking, tearing, or crushing a welded sample piece to see how much extreme force it can handle before failing. Because the test piece is completely destroyed, this method is obviously never used on the final product going to the customer. Instead, we use these violent destructive tests on small sample plates during the qualification phase to prove that a written welding procedure actually works in reality. The most common destructive test you will encounter is the tensile test. In a tensile test, a massive hydraulic machine grabs both ends of a welded sample and slowly pulls it apart until it violently snaps in half. This test accurately measures the tensile strength of the weld, telling the engineer exactly how many pounds of pulling force the joint can survive. For your exam, remember that a successful tensile test usually requires the metal to break outside of the weld itself, proving the new weld is stronger than the original base metal. Another critical destructive method is the guided bend test. In this test, a small, flat strip of the welded metal is forced into a tight U shape by a heavy steel plunger. The primary goal of the bend test is to evaluate the ductility and soundness of the weld joint without necessarily breaking it completely in half. If the weld contains hidden cracks or lacks fusion, the extreme stretching on the outside of the bend will force those hidden microscopic defects to tear open and become clearly visible. You will also need to know about the Sharpe V-notch test, which we mentioned briefly in the previous metallurgy section. This test measures the extreme toughness of a weld by striking a small, notched sample piece with a heavy swinging metal pendulum. The machine calculates exactly how much impact energy the metal absorbs during the sudden violent strike before shattering. This specific test is heavily required for structures built in freezing environments, because cold temperatures naturally make steel more brittle and prone to catastrophic shattering. Moving on, we enter the world of non-destructive testing, commonly abbreviated as NDT in the industry. Non-destructive testing allows us to examine the internal and external structure of a finished weld without damaging it in any way. This means we can scan the exact pipe or bridge column that will be used in the real world to guarantee it is completely safe for the public. As a certified welding inspector, coordinating and interpreting these non-destructive tests will be a massive part of your daily responsibilities on the job site. Visual inspection is technically the first and most important method of non-destructive testing. A trained inspector using just their eyes, a bright flashlight, and a few simple measuring gauges can catch the vast majority of welding defects before they become serious problems. Visual inspection is so critical that almost all standard welding codes require a weld to completely pass a visual check before any other testing methods are allowed to begin. If a weld looks terrible on the surface, there is no reason to spend money scanning the inside. Beyond simple visual checks, liquid penetrant testing is an extremely popular and inexpensive method used to find tiny cracks on the surface of a metal. The inspector sprays a brightly colored red liquid dye onto the weld and gives it time to soak deeply into any invisible surface cracks. After carefully wiping away the excess liquid, a white developer powder is sprayed over the area, which acts like a microscopic sponge to pull the trapped red dye back out. This creates a bright, highly visible stain exactly where the hidden crack is located. Keep in mind that liquid penetrant testing has a major limitation that you will very likely see on your exam. This method can only detect defects that physically break the outer surface of the metal, meaning it cannot find a crack buried deep inside the weld joint. However, it is incredibly useful because it can be used on almost any non-porous material, including non-magnetic metals like stainless steel and aluminum. It is highly portable, very cheap, and incredibly easy to perform on a busy, crowded construction site. For magnetic materials like standard carbon steel, we often use magnetic particle testing. In this method, the inspector uses a powerful electromagnetic yoke to create a strong magnetic field flowing directly through the welded joint. They then dust very fine iron powder over the area, which is instantly drawn to any disruptions in the magnetic field caused by tiny cracks. The iron powder literally piles up directly on top of the crack, creating a clear, visible outline of the defect for the inspector to see. Magnetic particle testing is excellent because it can find surface cracks and also defects located slightly below the surface of the metal. However, an essential exam fact to remember is that this method only works on ferromagnetic materials, meaning materials that a magnet will naturally stick to. You absolutely cannot use magnetic particle testing on aluminum, copper, or most standard stainless steels. Always verify what kind of metal you're inspecting before choosing to apply this specific testing method. When we need to look deep inside thick metal, we turn to radiographic testing, which is essentially industrial X-ray testing. A highly trained technician places an X-ray film on one side of the weld and shoots powerful radiation through the metal from the exact opposite side. This creates a highly detailed black and white picture of the inside of the weld, similar to a medical X-ray of a broken bone. Porosity, trapped slag, and deep internal cracks will appear as dark spots on the bright film because they are less dense than the solid steel. Radiographic testing produces a permanent physical record of the weld quality, which engineers love because they can review the actual film years later. However, working with powerful radiation on a job site is extremely dangerous and requires strict safety perimeters to protect the surrounding workers. Additionally, X-rays are very expensive, slow to produce, and require specialized film viewing equipment to read the results accurately. As an inspector, you will often review these dark films to ensure the X-ray technician interpreted them correctly. Another incredibly powerful internal scanning method is ultrasonic testing. This advanced method uses high-frequency sound waves, completely inaudible to human ears, to literally listen for defects deep inside the solid metal. A technician slides a small electronic probe over the weld, which sends rapid pulses of sound energy down into the steel joint. If the sound wave hits a hidden crack, it bounces back to the surface probe like a canyon echo, and the machine displays the defect on a digital screen. Ultrasonic testing is heavily favored for thick, heavy structures because sound waves can easily penetrate deep into solid metal where traditional X-rays might struggle. It is also completely safe for the surrounding workers, meaning the busy construction site does not have to shut down during the testing process. However, reading the bouncing digital echo signals requires an immense amount of training and operator skill. The final results are highly dependent on the experience of the technician holding the probe, which is a major factor to consider on your exam. Every non-destructive testing method has unique strengths and critical limitations that you must understand. For example, X-rays are fantastic for finding round holes of porosity, but they can easily miss a flat, microscopic crack if the radiation hits it from the wrong angle. Ultrasonic testing, on the other hand, is extremely sensitive to flat cracks, making it the perfect tool to catch defects that X-rays might leave behind. Understanding this complementary relationship between testing methods is vital for any certified welding inspector. It is highly important to remember that non-destructive testing technicians are usually certified under their own separate system, such as the ASNT guidelines. While you, as a certified welding inspector, may not personally shoot the dangerous X-rays or run the complex ultrasonic probes, you must understand their basic mechanics. You are often the final authority on the project, meaning you must be able to read their testing reports, verify their calibration methods, and ensure they are following the correct code requirements. When a defect is finally found by any of these testing methods, the inspector must compare its size to the strict acceptance criteria listed in the governing welding code. Not every tiny flaw requires a repair, and unnecessarily grinding out a harmless imperfection can actually do more damage to the metal than leaving it alone. The welding code acts as the supreme law book, telling you exactly how long or deep a crack can be before it officially becomes a rejectable defect that must be fixed. To summarize this dense topic, destructive testing scientifically proves that a welding recipe is strong and sound before the real work ever begins. Non-destructive testing is then used to carefully scan the final product to ensure the welder followed that exact recipe perfectly. Together, these two broad categories of testing provide the solid physical evidence needed to sign your name on an official inspection report with complete confidence. Mastering when and how to apply these specific tests will make you an incredibly valuable asset to any heavy engineering team. Congratulations on completing this essential section on destructive and non-destructive testing methods. I strongly encourage you to complete the attached practice test right away while the information is fresh. Completing practice questions immediately after the lesson improves your memory retention and builds the real exam readiness you absolutely need. Mentioning again, the practice test is included right here with this lesson, so please use it to trigger your active learning. End this session positively, take a quick mental break, and we will naturally transition into welding safety, symbols, and documentation in the next section. Welcome back to the fourth section of our course, focusing on welding safety, symbols, and documentation. In this lesson, you will learn the universal language of welding blueprints, the critical safety protocols required on every job site, and how to read the essential paperwork that governs our industry. Understanding these elements is absolutely vital because an inspector must protect their team and accurately interpret engineering designs before any welding begins. I am thrilled to walk you through this material because it is the practical glue that holds every major construction project together. Get your notebooks ready, focus your attention, and let us master these crucial skills. Let us begin with the most important topic on any job site, which is welding safety. As a welding inspector, you are not just looking for cracks in steel, you're also responsible for identifying immediate hazards that could harm you or the welders around you. The intense heat, bright light, and dangerous electrical currents involved in welding create a highly hazardous environment if not properly managed. For your exam, always remember that safety is the absolute first priority, and an inspector has the authority to stop work immediately if conditions become dangerous. The most immediate danger in arc welding is the intense ultraviolet and infrared light produced by the electric arc. This bright light is so powerful that it can literally sunburn the surface of your eyes in a matter of seconds, a painful condition commonly known as arc flash. To prevent this, everyone in the immediate area must wear proper eye protection equipped with specialized dark filter lenses. Inspectors and welders must always verify they are using the correct shade number for the specific welding process being performed, as higher amperages require much darker lenses for safe viewing. Another major safety concern is the inhalation of toxic welding fumes and hazardous gases. As the welding arc melts the metal and flux, it creates a rising plume of smoke that can contain dangerous particles like chromium, manganese, and ozone. Breathing these fumes over time can cause severe long-term health issues for the welder and the inspector standing nearby. This is why proper ventilation systems, such as local exhaust hoods or high-quality respirator masks, are strictly required when welding in confined spaces or poorly ventilated areas. Electrical shock and fire hazards are also constantly present when operating heavy industrial welding equipment. Welders are working with live electrical currents, meaning standing in a puddle of water or using frayed cables can quickly lead to a fatal electrocution. Furthermore, the flying molten sparks can easily ignite nearby flammable materials, which is why a dedicated firewatch person is often required to stand guard during welding operations. As an inspector, you must constantly scan the work area to ensure cables are undamaged and the surrounding environment is free of explosive hazards. Now we will transition into the universal language of the industry, which is the AWS welding symbol system. Engineers use these specific symbols on blueprints to tell the welder and the inspector exactly what kind of joint needs to be built. Instead of writing a long paragraph explaining the weld, the engineer draws a simple symbol that conveys the joint type, weld size, length, and exact location in a tiny space. Mastering these symbols is a massive part of the certification exam, and you must be able to decode them quickly and accurately. Every welding symbol is built upon two fundamental parts, which are the horizontal reference line and the pointing arrow. The arrow line simply points directly to the physical joint on the drawing where the weld needs to be placed. The horizontal reference line is the anchor for all the vital information, holding the specific geometric shapes and numbers that describe the weld. You can think of the reference line as a shelf where the engineer neatly organizes all the necessary instructions for the fabrication team. The most critical rule of reading a welding symbol is understanding the placement of information above or below the reference line. If a weld symbol is drawn below the reference line, it means the weld must be placed on the exact same side of the joint that the arrow is touching, known as the arrow side. If the symbol is drawn above the reference line, the weld must be placed on the opposite side of the joint, known as the other side. This simple above and below rule dictates the entire physical orientation of the welding project. The most common symbol you will see is the fillet weld, which is represented by a simple right triangle resting on the reference line. The vertical, straight leg of the triangle is always drawn on the left side of the symbol, regardless of which way the arrow points. The numbers placed immediately to the left of this triangle tell you the required size of the weld, such as a 1/4 inch or a 1/2 inch fillet. The numbers placed immediately to the right of the triangle tell you the required length of the weld. Groove welds have several different symbols depending on how the edge of the metal is prepared before welding. For example, a V-groove is represented by a simple letter V, while a bevel groove is represented by a line with one angled side, looking like half of a V. Just like the fillet weld, the numbers around these shapes provide critical dimensions, such as the required depth of preparation or the root opening gap. Recognizing the difference between a square groove, a V-groove, and a U-groove is heavily tested on the blueprint reading portion of the exam. Engineers also use supplementary symbols to add extra instructions to the main welding symbol. A common supplementary symbol is the weld all-around symbol, which is a small circle placed exactly where the arrow meets the reference line. This circle tells the welder to carry the weld completely around the entire perimeter of the joint without stopping. Another important supplementary symbol is the field weld flag, which is a small flag pointing away from the reference line, indicating the weld must be made out on the construction site rather than inside the fabrication shop. Sometimes the engineer needs to communicate special instructions that do not fit into the standard geometric shapes. They will add a small fork at the very end of the reference line called the tail. Inside this tail, the engineer can write a specific welding process like gas tungsten arc welding, reference a specific codebook, or list a particular welding procedure number that must be used. If no special instructions are needed for the joint, the tail is simply omitted from the drawing altogether. Moving from blueprints to paperwork, we must discuss the essential documentation that governs all industrial welding. No welder is allowed to simply guess how to weld a joint on a critical bridge or pressure vessel. Everything must be carefully planned, tested, and documented in a series of official forms before any sparks fly. The three main documents you will work with every single day are the Procedure Qualification Record, the Welding Procedure Specification, and the Welder Performance Qualification. The documentation process begins with the Procedure Qualification Record, commonly known as the PQR. Think of the PQR as the actual laboratory test results of a brand new welding recipe. The engineer writes a draft recipe, a welder attempts to weld it on a test plate, and then that plate is sent to the lab for destructive testing. The PQR document records the exact temperatures, amperages, and lab results of that specific test plate, proving with hard data that the new recipe actually works in the real world. Once the PQR proves the recipe is successful, the engineer creates the Welding Procedure Specification, or WPS. The WPS is the official instruction manual given directly to the welders on the shop floor. It lists all the permitted variables they are allowed to use, such as the required base metal, electrode type, voltage ranges, and shielding gas flow rates. As an inspector, checking that the welder is actively following the specific ranges listed on the WPS is one of your most critical daily responsibilities. Even if you have a perfect WPS, you still need to prove that the human being holding the torch is skilled enough to follow it. This requires the Welder Performance Qualification, often called the WPQ or the Welder Certification. The WPQ is a formal document proving that a specific welder passed a physical hands-on test using a particular welding process and position. An inspector must constantly check these WPQ documents to ensure every welder on site is actually certified for the specific joint they are attempting to build. Understanding the relationship between these documents relies entirely on the concept of essential variables, which we mentioned earlier in the course. If a change is made on the job site that violates an essential variable, such as switching from carbon steel to stainless steel, the existing WPS becomes completely invalid. The company must then go back to the beginning, weld a new test plate, send it to the lab, write a new PQR, and issue a brand new WPS to legally cover the change. Welding codes also define non-essential variables, which are minor changes that do not affect the mechanical strength of the final weld. An example of a non-essential variable is changing the brand name of the welding machine, or changing the style of the metal groove from a V groove to a U groove. If a non-essential variable changes, the company can simply update the written WPS document without having to spend money on expensive laboratory testing and a new PQR. Handling this paperwork properly is the true mark of a professional certified welding inspector. While spotting physical defects is important, ensuring the paper trail is flawless is what ultimately protects the company from massive legal liability. If a welded structure ever fails in the future, investigators will demand to see the WPS, the PQR, and the WPQ to verify everything was done legally. Your signature on the final inspection report legally verifies that all of this critical documentation was present and perfectly followed. Congratulations on completing this vital section covering welding safety, symbols, and documentation. I strongly encourage you to complete the attached practice test right now to lock in these complex concepts. Completing practice questions improves your long-term retention and ensures you are fully prepared for the heavy blueprint reading on the exam. I want to remind you that the practice test is included with this lesson, so please dive in and keep up your active learning momentum. Finish this module strong, take a well-deserved breather, and I will see you in the next section for practical inspection techniques. Welcome to the fifth section of our course, focusing on practical inspection and floor evaluation. In this lesson, you will learn how to use physical measuring tools to evaluate real welds and identify rejectable defects. This is incredibly important because a large portion of your actual certification exam requires hands-on visual inspection skills. I am excited to guide you through these practical techniques because they bridge the gap between textbook theory and real-world job performance. Get your inspection tools ready, focus your mind, and let us master the art of floor evaluation. Let us start by discussing the basic tools every certified welding inspector carries in their pocket. One of the most essential instruments is the fillet weld gauge, which is a small metal gauge used to quickly measure the leg length and convexity of a fillet weld. Another vital tool is the high clutch gauge, used to measure internal alignment and fit up gaps before any welding starts. Having reliable, calibrated physical tools ensures your measurements are accurate and defensible if anyone ever questions your inspection results. Visual inspection must always be conducted under proper lighting conditions to ensure tiny flaws are not missed in shadows. Industry codes usually require a minimum light intensity of 100-foot candles at the surface of the weld you're inspecting. Additionally, your eyes must be positioned at a favorable angle, usually no more than 30 degrees from the surface, and you must get within 24 inches of the weld. As an inspector, you cannot spot a hidden crack if you are standing too far away or working in a dark corner. One of the most common surface flaws you will encounter on the exam and in the field is undercut. Undercut is a sharp groove melted into the base metal right along the edge of the weld bead, where the welder failed to fill the gap completely. This defect is dangerous because it acts as a stress concentrator, meaning it concentrates all the structural load onto a tiny, thin line of metal. You must use a depth gauge to measure how deep the undercut goes, because welding codes strictly limit how much undercut is legally allowed. Another frequent visual defect is overlap, which happens when the weld metal rolls over the edge of the base metal without actually fusing to it. Unlike undercut, which is a groove, overlap is extra metal sitting loosely on top of the plate like a small shelf. This defect is easily caused by incorrect travel speed or poor torch angle, and it creates a built-in crack initiator that will fail under stress. Whenever you spot overlap during an inspection, it is automatically classified as a rejectable defect that requires grinding and repair. Porosity is another major issue, appearing as tiny gas pockets trapped inside or on the surface of the weld bead. Often called pinholes, surface porosity looks like a Swiss cheese pattern of tiny round holes breaking through the top of the metal. While scattered, microscopic internal porosity is sometimes tolerated by codes. Any porosity that breaks the surface of a highly stressed weld is usually rejected. The presence of surface porosity is a clear sign to the inspector that something went wrong with the shielding gas or the cleanliness of the metal. Slag inclusion is a defect unique to welding processes that use flux, such as stick welding or flux cord welding. This happens when chunks of solid flux become trapped inside the molten weld metal instead of floating safely to the top as a crust. Because slag is essentially glass-like waste material, it has zero structural strength and creates a massive weak spot inside the joint. As an inspector, you must watch for jagged black lines on X-ray films or surface chips that reveal trapped slag hiding beneath the final passes. Incomplete fusion is one of the most serious internal defects a welder can make. This happens when the welding arc fails to completely melt and bond with the sidewall of the base metal or the previous weld pass. Imagine trying to glue two pieces of wood together with dry glue sitting between them, and you have a clear picture of incomplete fusion. Because there is literally zero atomic bonding across that interface, an inspector must use ultrasonic testing or X-rays to catch this dangerous structural flaw. Incomplete penetration is closely related to fusion problems, but it specifically occurs at the very root of the joint. This defect happens when the weld metal fails to completely reach the bottom root opening of a groove weld, leaving a hollow gap at the back. If a pipe joint has incomplete penetration, it cannot withstand high internal fluid pressure and will eventually leak or rupture. Catching this during root pass inspection is a crucial responsibility for any inspector working on industrial piping systems. Cracking is universally considered the most dangerous and unacceptable defect in the entire welding industry. Unlike porosity or minor undercut, a crack has sharp, pointed ends that act as continuous stress multipliers under heavy loads. If a structure is left in service with an active crack, that crack will rapidly grow larger until the entire metal component snaps in half. For your certification exam, remember that any crack, regardless of its tiny size, is an automatic and immediate rejection. Welding cracks are generally divided into two main categories, known as hot cracks and cold cracks. Hot cracks happen at extremely high temperatures while the metal is still freezing solid, often caused by heavy shrinkage stresses pulling on weak liquid boundaries. Cold cracks happen hours or even days after the weld has completely cooled down to room temperature, usually driven by trapped hydrogen gas and brittle microstructures. As an inspector, knowing when and how these different cracks form helps you determine their root cause. Crater cracks are a specific type of hot crack that form right at the stopping point of a welding bead. When a welder suddenly snaps the arc out without filling the crater, a small circular depression forms with a tiny star-shaped crack right in the middle. These crater cracks are notorious for spreading across the entire weld if they are not properly ground out and re-welded. You must carefully inspect the endpoints of every long weld bead to ensure the welder properly filled the craters. Weld size is another critical parameter you must measure physically during your practical evaluation. For a fillet weld, you must verify both the leg size and the throat thickness to ensure it matches the engineering drawings. If a fillet weld is undersized, it lacks the cross-sectional area needed to carry the required load safely. If it is significantly oversized, the shop is wasting expensive filler metal and time, which is also flagged as an inefficiency during quality audits. Excessive reinforcement is a common defect where the welder builds up a massive, bulging hump of metal on top of a groove weld. While people often mistakenly think more metal always means a stronger joint, excessive reinforcement actually creates severe stress concentrations at the toes of the weld. Standard codes place a strict maximum limit on how high the weld reinforcement is allowed to stick up above the surrounding base plate. You must use a bridging gauge to measure this height accurately during your final inspection. Arc strikes are another subtle defect that inspectors frequently catch outside the actual joint area. A welder commits an arc strike when they accidentally brush their electrode against the clean base metal outside the weld zone, leaving a small burn scar. This localized spot melts instantly and cools rapidly into a hard, brittle patch of martensite that can easily start a fatigue crack under vibration. For structural components, you must check the surrounding plates for stray arc strikes and require them to be safely ground out and repaired. Lamination is a manufacturing defect found inside the base metal itself, rather than something the welder created. It appears as a flat, internal layer or split running parallel to the surface of the steel plate, caused by trapped impurities during the original steel rolling mill process. If a welder tries to attach a T-joint directly over a lamination, the intense heat will cause the metal to split open like the pages of a book. An inspector must check plate edges carefully before welding begins to spot laminations hiding in the material. When you encounter a rejectable defect, you must document it clearly and mark the exact location on the metal surface using special heat-resistant chalk or paint markers. You then issue a rejection notice that explains the specific code violation, giving the fabrication crew clear instructions on what needs to be repaired. Once the crew grinds out the defect and re-welds the area, you must re-inspect the repaired zone using the exact same testing methods to ensure the fix was successful. Practical inspection requires a sharp eye, total patience, and an uncompromising dedication to quality standards. You cannot let pressure from production managers rush you through a visual check, because public safety ultimately rests on your final approval signature. Developing a systematic inspection routine, where you check dimensions, cleanliness, profile, and defects in a set order, will make you fast, accurate, and reliable in the field. As you prepare for the practical portion of your certification exam, remember that confidence comes from hands-on familiarity with your tools and acceptance criteria. Practice measuring various weld profiles, identifying subtle flaws on sample plates, and navigating code acceptance tables until it becomes second nature. Your ability to evaluate flaws objectively is what transforms you into a truly elite certified welding inspector. Congratulations on completing this comprehensive section on practical inspection and flaw evaluation. I strongly encourage you to complete the attached practice test right away while your memory is sharp. Completing practice questions immediately after the lesson drastically improves your retention and locks in your exam readiness. The practice test is included right here with this lesson, so dive in to support your active learning journey. Once you master these practical concepts, we will naturally transition into the final code clinic and specification navigation in our next section. Welcome to the final section of our course, where we dive into the code clinic and specification navigation. In this lesson, you will learn how to efficiently navigate complex welding codes like AWS D1.1 and find specific answers under pressure. This is arguably the most important skill for passing Part C of your certification exam. I am thrilled to help you master this open book navigation because it turns a terrifying code book into a powerful tool. Get your code book ready, stay focused, and let us conquer the final hurdle together. Every certified welding inspector must rely on a governing code book to make official decisions on the job site. A welding code is a comprehensive rulebook created by engineering experts that dictates every legal requirement for design, fabrication, and inspection. The most common code you will use in structural steelwork is AWS D1.1, published by the American Welding Society. For pipeline work, you will likely use API 1104, while pressure vessels fall under the ASME boiler and pressure vessel code. One of the biggest mistakes candidates make on the exam is trying to memorize the entire codebook from cover to cover. Trying to memorize thousands of pages of rules, tables, and clauses is completely impossible and a massive waste of your study time. Instead, the exam is specifically designed to test your navigation skills, meaning it tests how fast and accurately you can find the correct answer in an open book. Your goal is not to be a walking encyclopedia, but to be a master navigator who knows exactly where to look. To navigate these massive documents efficiently, you must first understand how a welding code is structured and organized. Codes are typically divided into major sections called clauses, which cover broad topics like design, qualification, fabrication, and inspection. Each clause is then broken down into smaller parts called subclauses, paragraphs, and subparagraphs, designated by a specific numbering system. Learning this hierarchical layout is like learning the street map of a new city so you never get lost. At the very beginning of almost every major welding code, you will find a dedicated definitions section that is an absolute goldmine for exam questions. When a code uses a specific term like rejectable discontinuity, weld interface, or qualified position, it provides a precise, legal definition in this section. If you encounter an unfamiliar term during the exam, do not guess its meaning based on everyday English. Always check the code definition section to see how the authors legally defined that specific word. Another crucial section you must master early is the table of contents and the alphabetical subject index located in the back. The index is your fastest shortcut to finding specific topics during the timed exam sections. If a question asks about preheat requirements for high-strength steel, you should immediately flip to the back index, look under the letter P for preheat, and find the exact clause number. Practicing this lookup technique ahead of time will save you precious minutes on test day. Let us look closely at AWS D1.1, which is the structural welding code for steel used in buildings and bridges. This massive book covers everything from architectural fabrication requirements to the structural qualification of welding operators. Within D1.1, you will find specific tables that dictate the minimum preheat temperatures based on steel thickness and carbon content. As an inspector, knowing how to cross-reference these tables quickly ensures that fabrication meets strict engineering standards. Another vital area inside structural codes is the section covering structural repair procedures and allowable defect limits. When you find a rejectable crack or excessive porosity on a bridge girder, you cannot just let the crew guess how to fix it. You must open your codebook to the structural repair clause and read the exact criteria for excavation depth and re-welding approval. This ensures that every repair is legally compliant and restores the structure to its full load-bearing capacity. If your career takes you into the oil and gas sector, you will transition from structural codes to pipeline codes like API 1104. API 1104 focuses heavily on cross-country steel pipelines, pipeline girth, welds, and field inspection standards. The acceptance criteria in API 1104 are often based heavily on radiographic testing films rather than visual depth measurements alone. Understanding how to navigate pipeline standards is essential for inspectors working in remote energy fields. Pressure vessel inspection brings us into the realm of the ASME boiler and pressure vessel code, specifically Section 9 and Section 8. Section 9 governs the qualification of welding procedures and welders, while Section 8 covers the actual rules for manufacturing pressure vessels. These books use very specific terminology and cross-reference each other constantly, making navigation a true test of patience and precision. Mastering ASME navigation opens up some of the highest-paying inspection roles in the manufacturing industry. When reading code paragraphs, you must pay extreme attention to the specific auxiliary verbs used by the authors, such as shall and should. In engineering codes, the word shall always indicates a mandatory, non-negotiable requirement that you must enforce on the job site. The word should, on the other hand, indicates a recommendation or best practice that is strongly advised but not legally mandatory. Misinterpreting a shall for a should can lead to massive legal liabilities and failed structural audits. Codes also frequently use tables and charts to summarize complex data into easy-to-read grids. To read a code table correctly, you must start by reading the title and the main column headings to understand what data is being compared. Then, follow the rows across to match your specific variable, such as metal thickness or welding process, to find the intersecting value. Practicing table lookups will ensure you never misread a critical engineering limit during a high-pressure exam. Another advanced code skill is understanding mandatory versus non-mandatory annexes located at the back of the book. Mandatory annexes carry the exact same legal weight as the main body clauses and must be followed when applicable. Non-mandatory annexes provide helpful guidelines, recommended practices, or extra background information, but they are not strictly required unless specifically invoked by the contract documents. Knowing the difference prevents you from enforcing unnecessary rules on a fabrication crew. During the CWI exam, time management is your greatest enemy because you have a massive amount of reading to complete in a limited window. This is why experienced instructors recommend tabbing your codebook with color-coded sticky notes before entering the exam room. Placing physical tabs on major clauses, frequently used tables, and the index allows you to flip directly to the right page in seconds. Preparing your physical book properly is just as important as studying the actual theory. When tackling a difficult code question, always start by reading the question stem very carefully to identify the core keyword. Once you spot the keyword, find the relevant clause in your index, flip to that page, and read the surrounding paragraphs completely. Never rely on memory alone for code questions, because codes are frequently updated with new revisions, and old rules can change. Always verify your answer by physically pointing your finger at the text in the open codebook. Codebooks are updated every few years to reflect new technology, modern materials, and improved safety standards discovered by engineering research. As a certified welding inspector, you must stay current with these revisions to ensure your inspections comply with the latest legal additions. Relying on an outdated codebook on a modern construction project can result in catastrophic failures and severe legal consequences for your inspection agency. Becoming truly fluent in code navigation takes patience, regular practice, and a systematic approach to reading technical writing. Set aside dedicated study hours to practice looking up obscure code clauses under a simulated timed environment before your exam date. The more comfortable you become with flipping pages and cross-referencing tables, the more confident and relaxed you will feel on test day. Your journey through this comprehensive course has equipped you with the foundational welding processes, metallurgical science, testing methods, safety rules, and inspection skills. Mastering code navigation is the final master key that unlocks your certification and opens the door to an elite career. Take pride in how far you have come, because you now possess the knowledge base of a true professional. As you wrap up your final review, remember that passing the CWI exam is entirely within your grasp if you stay disciplined and focused. Keep practicing your code navigation, review your flashcards, and trust in the thorough preparation you have built throughout this course. You are fully capable of earning your certification and stepping into a rewarding, highly respected inspection career. Congratulations on completing the entire AWS Certified Welding Inspector preparation course. I strongly encourage you to complete this final practice test right now to lock in your code navigation mastery. Completing practice questions immediately after the lesson drastically improves your retention and ensures total exam readiness. This final practice test is included right here with this lesson, so dive in to complete your active learning journey. Finish this course strong, trust your preparation, and go ace your certification exam with absolute confidence.